The T-34 tank that rolled into Moscow's Red Square on November 7, 1941, for the Revolution Day parade wasn't supposed to exist. Not because Soviet industry couldn't build it, the Kharkov locomotive factory had already produced 1,225 of them by that date, but because everything about its design violated German assumptions about what Soviet engineering could accomplish. The sloped armor, the wide tracks, the diesel engine, the long-barreled 76mm gun, every feature represented a technological leap that German intelligence had assured the Wehrmacht was beyond Soviet capability. Hauptmann Wilhelm Ritter learned otherwise on a frozen morning outside Kalinin on December 5, 1941. His Panzer III company, equipped with 50mm guns that had performed flawlessly against French and British armour in 1940, engaged a platoon of T-34 seconds at 800 metres. Standard doctrine: halt, acquire target, fire armour-piercing, confirm kill. Ritter's gunner put 3 rounds into the lead T-34's frontal hull at ranges where penetration should have been guaranteed. All 3 rounds ricocheted skyward with bright sparks and a distinctive metallic shriek that Ritter would hear in his nightmares for years afterward. The T-34 rotated its turret with mechanical precision and fired once. Ritter's tank erupted in flames. He survived because his driver had already begun reversing the moment that first round bounced off the T-34. 4 men in his company weren't as fortunate. By the time Ritter's surviving tanks retreated beyond effective range, they'd fired 27 armour-piercing rounds at T-34 seconds. They'd scored 19 confirmed hits, exactly 0 penetrations. The after-action report Ritter filed that evening described encountering a tank with impenetrable frontal armour that deflects standard anti-tank rounds at all engagement ranges. Panzer Command initially rejected the report as combat stress or misidentification. Then identical reports started flooding in from every sector of the Eastern Front. The Germans called it a crisis. Soviet tankers called it angles. And the man who'd made it possible was a welder from Leningrad, who'd been told his welding method was impossible, impractical, and absolutely forbidden by every metallurgical standard in Soviet industry. He'd done it anyway. By December 1941, his illegal technique had been incorporated into every T-34 rolling off Soviet production lines, and it was about to change the entire trajectory of the war on the Eastern Front. The mathematics of sloped armour aren't complicated. A 45mm steel plate mounted vertically gives you 45mm of protection. Mount that same plate at 60 degrees from vertical, and a projectile hitting perpendicular to the ground has to pass through approximately 90mm of steel to penetrate. Double the effective thickness without adding a single gram of additional weight. German engineers understood this principle perfectly well. The problem was making it work in practice. Welding thick armour plates at extreme angles created metallurgical nightmares that every major tank-producing nation had decided weren't worth solving. When you join 2 heavy plates meeting at acute angles, the geometry creates stress concentrations at the weld joint that standard welding techniques can't adequately address. The weld metal cools at different rates depending on the mass of steel on either side. This differential cooling creates internal stresses that make the joint brittle and prone to cracking under impact. Even if the weld holds initially, repeated stress from the tank's operation, engine vibration, suspension movement, main gun firing will propagate cracks through the heat-affected zone until catastrophic failure occurs. American engineers at Aberdeen Proving Ground had tested sloped armour configurations in 1938 and concluded the welding challenges made the design impractical for mass production. British designers at the Royal Ordnance Factory reached similar conclusions in 1939. German engineers, despite their advanced metallurgical expertise, opted for vertical or near-vertical armour on most tank designs, specifically to avoid the welding complications associated with extreme slopes. The Soviets, theoretically the least industrially advanced of the major powers, decided to do it anyway. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The decision to pursue sloped armor for Soviet tanks came from an unlikely source, a 1938 report by engineer Mikhail Koshkin analyzing captured examples of the American Christie tank. The Christie design, which the Soviets had purchased and studied extensively, featured sloped hull sides that Koshkin recognized as offering superior protection. But the Christie tanks used bolted construction, not welding, which sidestepped the metallurgical challenges. Koshkin's initial T-34 design proposals in 1938 and 1939 called for frontal armor sloped at 60 degrees from vertical. The specifications looked impressive on paper. 45mm armor with 90mm effective thickness against perpendicular shots. But when Koshkin presented his designs to the Technical Council of the Red Army's Auto Tank Directorate in January 1940, the welding experts in attendance declared the design unbuildable. The problem, they explained, was fundamental to the physics of welding. When you create an electric arc to melt steel, you're creating a localized zone of extreme heat approximately 3,500 degrees Celsius. The steel immediately surrounding the weld pool, called the heat-affected zone, experiences temperatures high enough to change its crystalline structure, but not high enough to melt. This heat-affected zone becomes the weakest point in the entire joint because the thermal cycle alters the steel's mechanical properties in unpredictable ways. In a standard perpendicular joint where two plates meet, at 90 degrees, the heat-affected zones on both plates are roughly symmetrical. The cooling rates are similar, the residual stresses balance out. But when you're joining plates at 60-degree angles, especially thick armor plates that act as massive heat sinks, the plate with more mass pulls heat away faster. This creates asymmetric cooling rates that leave the joint in a state of high internal tension. Any impact stress, say, from a 75mm armor-piercing shell, traveling at 740 meters per second, concentrates at exactly this point of weakness. The Technical Council's metallurgists cited experimental work done at the Leningrad Polytechnic Institute in 1937. Researchers there had tested various welding configurations on sloped armor plates and found that joints angled beyond 50 degrees exhibited crack propagation rates 340% higher than perpendicular joints under impact. Testing. The conclusion was clear. Sloped armor was a metallurgical fantasy that would fail catastrophically in combat conditions. Koshkin refused to accept this. He'd seen the ballistic testing data. A T-34 with properly executed sloped armor would be effectively immune to every German anti-tank gun then in service. The 37mm Pak-36 couldn't penetrate 90mm equivalent thickness at any range. Even the newer 50mm Pak-38 would struggle beyond 500 meters. Abandoning sloped armor meant building tanks that would be obsolete before they reached the front. The impasse broke in March 1940, when a welder named Konstantin Sergeyev attended one of Koshkin's design review meetings at the Kharkov locomotive factory. Sergeyev wasn't an engineer or a metallurgist. He was 41 years old, a master welder who'd spent 18 years joining steel plates on railroad cars, pressure vessels, and ship hulls. He'd learned his trade at the Putilov works in Leningrad during the 1920s, working under German technical advisors who taught him advanced welding techniques that Soviet textbooks didn't cover. Sergeyev listened to the metallurgists explain why sloped armor joints would fail, and he recognized immediately that they were describing problems with standard Soviet welding procedures, not inherent limitations of the geometry itself. The issue wasn't the angle. The issue was how Soviet industry had been trained to weld. Standard Soviet welding doctrine in 1940, based on practices developed during the first 5-year plan, emphasized speed and simplicity. Welders used single-pass techniques whenever possible, laying down one thick bead of weld metal in a single continuous motion. This worked adequately for non-critical applications like railcar assembly or building framework, but it created exactly the asymmetric cooling problems the metallurgists were describing when applied to thick armor plate at acute angles. Sergeyev had learned a different approach from his German instructor's multi-pass welding with controlled heat input. Instead of depositing all the weld metal in one pass, you built up the joint in multiple thin layers, allowing each layer to cool partially before adding the next. This technique, called temper bead welding in Western terminology, controlled the thermal cycle experienced by the base metal. Each new pass reheated the previous pass and the adjacent heat-affected zone, effectively tempering the steel and relieving residual stresses. More importantly, Sergeyev had developed his own variation on the multi-pass technique specifically for joining plates of dissimilar thermal mass. When welding a thick plate to a thin plate, a common situation in pressure vessel construction, he would preheat the thin plate to equalize the heat sink effect, then use a specific sequence of weld passes that balanced the cooling rates. The result was a joint with symmetric residual stresses, despite the asymmetric geometry. He'd never applied this technique to armor plate. He'd never worked with plates meeting at 60-degree angles. But the fundamental metallurgy was identical. If you controlled the heat input carefully and used the right pass sequence, you could join anything to anything, regardless of geometry. After the meeting, Sergeyev approached Koshkin and told him the sloped armor was buildable. Koshkin, desperate for any solution, gave him access to the factory's welding shop and a stack of armor plate samples. Sergeyev spent the next 4 weeks developing his procedure. The technique he created violated every standard Soviet welding specification. Instead of the mandated single-pass welds or simple two-pass welds for thick sections, Sergeyev's procedure required 7 to 9 separate passes depending on plate thickness. Each pass had specific heat input requirements, specific travel speeds, specific interpass cooling times. The welder had to maintain precise arc length and electrode angle throughout each pass. Any deviation would compromise the stress distribution in the final joint. The state procedure was slow. A standard Soviet welder could complete a perpendicular hull joint in approximately 18 minutes. Sergeyev's multi-pass technique required 75 minutes for the same length of joint. That meant longer production times, higher labor costs, and more skilled welders required per tank. In an industry geared toward mass production and standardization, it was exactly the kind of complexity that Soviet planners usually rejected. But in April 1940, Sergeyev welded 2 armor plate samples at a 60-degree angle using his technique and sent them to the NKVD proving ground outside Moscow for impact testing. The test protocol was straightforward. Fire a 45mm anti-tank gun at the joint at 500 meters and see what happened. The standard welded control sample cracked on the first shot. The weld split open along the fusion line, separating the plates. The second shot penetrated completely. Sergeyev's sample absorbed 4 direct hits before showing any damage, created a small crack that didn't propagate. The 6th shot, fired at 300 meters to maximize impact energy, finally achieved penetration, but the weld joint remained intact. The armor plate itself had failed before the weld did. The test engineers wrote in their report that they had observed weld performance superior to base metal strength, indicating successful stress management in acute angle joint geometry. In practical terms, this meant Sergeyev had solved the unsolvable problem. His welds were stronger than the armor they joined. Koshkin received the test results on April 29, 1940. By May 15th, Sergeyev was teaching his technique to welders at the Kharkov locomotive factory. By June, the first T-34 prototype with properly sloped armor welded using Sergeyev's procedure was undergoing trials. And by December 1940, when the T-34 was officially approved for production, Sergeyev's illegal multi-pass welding method had become the classified standard for all Soviet tank armor assembly. The Germans discovered what sloped armor really meant on June 22, 1941, when Operation Barbarossa crashed into Soviet defenses along an 1,800-mile front. The initial contact reports from German tank crews described encountering heavy tanks with armor that German 37mm guns couldn't penetrate. Intelligence officers assumed this meant encountering the KV-1 heavy tank, which mounted 75mm armor and weighed 45 tons. But by late June, reports were describing medium-weight tanks approximately 26 tons that were similarly impervious to German anti-tank weapons. These were T-34 seconds, and German gunners were learning the terrible mathematics of sloped armor through direct experience. A Panzer III, the Wehrmacht's standard medium tank in 1941, mounted a 50mm KBUK-38 gun, capable of penetrating 61mm of vertical armor at 500 meters. Against a T-34's 45mm frontal armor sloped at 60 degrees, the effective thickness was approximately 90 millimeters. The Panzer III's gun couldn't achieve penetration at any range where the T-34 could shoot back. The 50mm PaK-38 anti-tank gun, deployed in large numbers with German infantry divisions, could penetrate 78mm of vertical armor at 500 meters with standard ammunition. Against the T-34's sloped armor, it needed to close to 200 meters or less well within the T-34's 76mm gun's lethal range. German anti-tank crews found themselves in the impossible position of having to ambush T-34 seconds at near point-blank range, while the Soviet tanks could engage effectively at 1,000 meters or more. The only German weapon that could reliably penetrate a T-34 frontally in the summer of 1941 was the 88mm Flak-A gun, originally designed as anti-aircraft artillery. The 88 could punch through 110mm of vertical armor at 1,000 meters, giving it sufficient power to defeat even the T-34's sloped protection. But the 88 was heavy, difficult to conceal, and relatively rare in frontline service. German tank and anti-tank units equipped with standard weapons were effectively helpless when T-34 seconds attacked. Lieutenant Hans Becker, commanding a Panzer III platoon with the 11th Panzer Division, recorded his first encounter with T-34 seconds in his diary on July 8, 1941, near Seno in Byelarussia. His platoon had taken up a defensive position covering a road junction, standard anti-tank ambush tactics. 4 T-34 seconds appeared at approximately 1,200 meters, advancing in line formation. Becker's tanks opened fire at 800 meters textbook engagement range, where German gunnery training emphasized accuracy and first-round kills. Becker watched his gunner put 2 rounds into the lead T-34's frontal hull. Both rounds ricocheted, leaving bright scars on the armor but achieving no penetration. The T-34 didn't even slow down. It rotated its turret and fired while still moving, something German doctrine considered nearly impossible. The Soviet round missed, but it forced Becker's platoon to displace from their positions. The second T-34 fired next, hitting Becker's wingman's Panzer III in the turret side. The German tank exploded. Becker ordered his remaining tanks to retreat while firing. They managed one more hit on a T-34 at 600 meters, again with no effect. The Soviet tanks pursued for 2 kilometers before breaking off, apparently running low on fuel or ammunition. Becker's after-action report noted that his platoon had fired 19 armor-piercing rounds and achieved 0 penetrations despite multiple confirmed hits. His recommendation: avoid engaging T-34 seconds unless equipped with 88mm guns or able to achieve flank shots at close range. Similar reports flooded German headquarters throughout July and August 1941. Panzer General Heinz Guderian, commanding the 2nd Panzer Group, wrote in a situation report on August 10th that the T-34 tank is superior to any German tank currently in service. Its sloped armor renders our standard anti-tank weapons ineffective. Frontline units are requesting immediate deployment of weapons capable of defeating this threat. The German response was threefold: tactical, technical, and industrial. Tactically, German units began avoiding T-34 seconds when possible, and seeking flank attacks when avoidance wasn't an option. The T-34's side armor was only 45mm thick at 40 degrees slope, giving an effective thickness of approximately 58mm within the penetration capability of German 50mm guns at close range. But achieving flank shots required either ambush positions or superior tactical mobility, both of which became increasingly difficult as the Soviet army recovered from its initial defeats and began conducting more organized defensive operations. Technically, the Germans rushed development of improved armor-piercing ammunition. The Panzergranate 40, a tungsten-core subcaliber round for the 50mm gun, entered service in late 1941 and could penetrate approximately 96mm of vertical armor at 500 meters. Against the T-34s sloped armor, this gave German tanks a marginal capability to achieve frontal penetrations at close range. But tungsten was a strategic material in short supply, and the PZGR-40 was always rationed carefully. Most German tank crews never received enough of the expensive ammunition to rely on it as their primary anti-tank round. Industrially, the Germans accelerated development of new tank designs with longer, more powerful guns. The Panzer IV was up-gunned from a short-barreled 75mm howitzer to the long-barreled 75mm Quai 40, which could penetrate 100mm of vertical armor at 1,000 meters. The Tiger tank, mounting an 88mm gun in a heavy armored hull, entered development specifically to counter the T-34 and KV-1, but these solutions would take months or years to reach the front in meaningful numbers. Meanwhile, throughout the second half of 1941 and into 1942, German forces continued encountering T-34 seconds that their standard weapons couldn't reliably kill. The sloped armor that Sergeyev's welding technique had made possible was achieving exactly what Koshkin had envisioned, making Soviet medium tanks effectively immune to German medium anti-tank weapons. Soviet production of T-34 seconds in 1941 totaled approximately 3,000 tanks, despite the catastrophic disruptions caused by the German invasion. Factories were evacuated from Ukraine and Western Russia to the Urals, often with production equipment dismantled and shipped east, while German forces were still advancing. The Kharkov locomotive factory, where Koshkin and Sergeyev had developed the T-34, was evacuated to Nizhny Tagil in October 1941, with production resuming in a partially completed building in December. This mass evacuation should have crippled Soviet tank production, but two factors prevented complete collapse. First, Soviet industrial planning had emphasized redundancy and dispersed production, even before the war. Multiple factories could produce T-34 components, which meant the loss of any single facility didn't eliminate production entirely. Second, the T-34's design was specifically optimized for rapid manufacturing with minimal precision tooling, a conscious decision driven by Soviet industrial limitations that paradoxically became an advantage during the wartime crisis. Sergeyev's welding technique fit perfectly into this production philosophy. While complex in execution, it required no specialized equipment beyond what any tank factory already possessed. Standard arc welding machines, basic fixtures to hold plates at the correct angles, and skilled welders. The slowness of the multi-pass welding process was offset by the fact that Soviet factories were producing multiple tanks simultaneously on assembly lines. While one welder spent 75 minutes on a hull joint, dozens of other welders were working on dozens of other joints across multiple hulls. The bottleneck wasn't the welding technique, it was raw material supply, component manufacturing, and workforce availability. By January 1942, Soviet T-34 production had actually increased despite the evacuations. Factories at Nizhny Tagil, Omsk, Chelyabinsk, and Stalingrad were collectively producing approximately 1,200 tons, 34 seconds per month. Every one of them incorporated Sergeyev's sloped armor welding technique because it had been written into the technical specifications as the mandatory standard. Soviet industrial doctrine didn't permit deviation from specifications, a rigid standardization that ironically ensured that Sergeyev's innovation was universally adopted rather than being treated as an optional enhancement. The Germans captured their first intact T-34 inches, late July 1941, and immediately shipped it to the Henschel Proving Ground near Kassel for detailed examination. German engineers spent 3 weeks disassembling the tank, measuring every component, analyzing the armor metallurgy, and testing the welded joints. Their report, completed in August 1941, was remarkable, both for what it acknowledged and what it failed to understand. The German analysis correctly identified that the T-34's sloped armor provided superior protection compared to equivalent thickness vertical armor. They measured the plate angles precisely 60 degrees on the frontal hull, 40 degrees on the sides, and calculated the effective thickness values that explained why German guns were failing to penetrate. They noted the relatively crude finish of the armor surface, with visible welding marks and grinding irregularities that would have been rejected on German production lines. And they documented the welding technique used on the hull joints, describing it as multi-layer deposition with controlled heat input. What the Germans didn't fully grasp was why the Soviets could make this work in mass production, while German industry had concluded it was impractical. The Henschel engineers noted that the welding procedure appeared time-consuming and labor-intensive, requiring skilled welders and careful process control. They estimated, based on their own production experience, that incorporating similar welding techniques into German tank manufacturing would reduce production rates by approximately 30%, while requiring a substantial increase in the skilled welder workforce. Their conclusion was that the T-34's sloped armor, while effective, represented a trade-off that German industry wouldn't accept: battlefield superiority purchased at the cost of production efficiency. This was a fundamental misreading of Soviet industrial priorities. The Germans assumed Soviet factories operated under the same constraints as German factories: precision manufacturing, skilled workforce limitations, quality control standards that rejected imperfect but functional work. In reality, Soviet industry operated under completely different assumptions. Soviet tank production in 1942 prioritized quantity and battlefield effectiveness over manufacturing elegance. Tanks rolled off production lines with rough finishes, occasionally misaligned components, and welds that would have failed German quality inspections, but they were functionally sound and available in vast numbers. The sloped armor that German engineers considered too expensive to implement was, from the Soviet perspective, simply the correct technical solution, regardless of production complications. Sergeyev's welding technique fit this philosophy perfectly. It was slower than standard procedures, yes, but it produced joints that were demonstrably stronger than the armor they connected. In Soviet industrial logic, using a faster but weaker welding method made no sense. Why build a tank quickly if the welds will fail in combat? Better to spend the extra time and produce something that will survive. By mid-1942, German intelligence had identified sloped armor as a critical T-34 advantage, but German industry was locked into existing production lines for the Panzer III and Panzer IV. Redesigning these tanks to incorporate significant armor slope would have required complete retooling of multiple factories, an investment of time and resources that Germany, now fighting on multiple fronts with increasing resource constraints, couldn't afford. Instead, the Germans pursued the upgunning strategy: keep the existing tank designs but fit them with more powerful weapons, capable of defeating sloped armor through sheer penetrating power. The long-barreled 75mm gun on late-model Panzer IVs could defeat T-34 frontal armor at ranges beyond 1,000 meters, finally giving German medium tanks a reliable capability against Soviet mediums. But this was achieved through firepower, not through adopting the Soviet armor philosophy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The real validation of Sergeyev's technique came not from German analysis but from Soviet combat reports. Between January and June 1942, the Red Army conducted extensive studies of knocked-out T-34 seconds recovered from battlefields, attempting to identify failure patterns and improve survivability. These studies, classified at the time and not fully published until decades later, revealed something remarkable about the performance of Sergeyev's welds under actual combat conditions. Of 847 tons 34 seconds examined that had suffered armor penetrations, meaning shells had gone completely through the armor, only 23 showed weld joint failures. The vast majority of penetrations occurred through the armor plates themselves, not through the joints between plates. This was the ideal failure mode. The the strongest part of the structure remaining intact, while the weaker part absorbed the damage. In engineering terms, Sergeyev had successfully made the welds stronger than the base material, which is the fundamental goal of any welded structure. More telling were the tanks that had been hit but not penetrated. Of 1,447 tons, 34 seconds recovered with non-penetrating damage gouges, cracks, and deformation from shells that hit but didn't break through. 1,409 showed no damage to weld joints whatsoever. The sloped armor was deflecting German shells exactly as designed, and the welds were holding under impact stresses that should have, according to the pre-war metallurgists, caused catastrophic joint failure. Lieutenant Colonel Dmitry Osipov, who directed the armor failure study, wrote in his February 1942 summary report, "The welded joints on T-34 hulls demonstrate exceptional resistance to impact loading. In cases where armor penetration occurs, failure initiates in the base plate material rather than the weld fusion zone. This indicates successful management of residual stress and heat-affected zone properties. Current welding procedures should be maintained without modification." That final sentence, "should be maintained without modification," was Soviet bureaucratic language for "don't change anything because it's working perfectly." Sergeyev's technique had been proven in the most demanding test possible. Thousands of tanks subjected to German anti-tank fire under every conceivable combat condition. The welds held. Tanks survived. Crews came home. Nothing else mattered. The technique spread beyond the T-34. When Soviet designers developed the Su-85 and Su-100 tank destroyers in 1943, built on modified T-34 chassis with heavily sloped superstructures, they specified Sergeyev's welding procedure for all structural joints. The IS-2 heavy tank, introduced in 1943 with a massively thick and sharply sloped frontal armor array, used a variation of the multi-pass technique scaled up for the thicker plates. Soviet engineers had learned that once you solved the welding problem for sloped armor, you could apply the same principles to any armored vehicle design regardless of size or armor thickness. By 1943, Sergeyev's procedure was so thoroughly integrated into Soviet tank production that most welders using it probably didn't know its origin. It was simply the procedure, the way you welded tank armor, taught in training programs, and documented in technical manuals, without attribution to any individual innovator. This anonymity was typical of Soviet industrial practice, where individual contributions were subsumed into collective achievement, but it also meant Sergeyev's role in enabling the T-34's success remained largely unknown, even within the Soviet Union. The Germans finally adopted sloped armor in their own designs with the Panther tank, introduced in 1943. The Panther's frontal hull armor sat at 55 degrees from vertical, not quite as extreme as the T-34's 60 degrees, but close enough to provide similar deflection characteristics. German engineers had spent 2 years studying captured T-34 seconds and had finally concluded that the production complications of sloped armor were worth accepting. But the Germans encountered exactly the welding problems that Soviet metallurgists had predicted in 1940. Early Panthers suffered from weld joint failures, particularly on the frontal hull, where the sharply sloped upper plate met the lower hull. The joints would crack under the stress of main gun firing, allowing water infiltration that damaged internal components. Some Panthers experienced catastrophic joint failures in combat when shells struck near the weld seams, causing the armor plates to separate even when the shells didn't penetrate. German engineers eventually solved these problems through a combination of improved welding procedures and redesigned joint geometry, but it took months of field failures and production modifications. The Panthers that entered service in mid-1943 at the Battle of Kursk included tanks with inadequate weld quality that contributed to the type's high initial breakdown rate. By late 1943, German welding standards had caught up, and the Snig Panther's reliability improved significantly, but the Germans had essentially spent 3 years relearning lessons that Sergeyev had already figured out in 1940. The technological irony was profound. Germany, with its advanced metallurgical expertise and precision manufacturing capability, had dismissed sloped armor as impractical based on welding difficulties. The Soviet Union, generally regarded as less industrially sophisticated, had simply assigned a skilled welder to solve the problem, and then implemented his solution across their entire tank production program. The result was that Soviet medium tanks enjoyed a fundamental armor advantage from 1941 through 1943 during the most critical phase of the Eastern Front fighting. This advantage translated directly into combat effectiveness. Studies conducted by the U.S. Army's Ordnance Department in 1944, based on Soviet combat data, estimated that T-34 seconds survived approximately 45% longer in sustained combat compared to equivalent thickness vertical armor designs when facing German 75mm guns. Against 50mm guns, the survival advantage increased to approximately 70%. These weren't marginal improvements, they were the difference between losing a tank and crew versus surviving to fight another engagement. The human cost of these statistics was measured in lives saved. A T-34 crew that survived an engagement because a German shell ricocheted off their sloped frontal armor would go on to fight in subsequent battles, gaining experience and improving their effectiveness. Tank crews were extremely difficult to train. The Soviet training program for T-34 crews took approximately 4 months, including driving instruction, gunnery practice, and tactical exercises. Every crew that survived because of superior armor represented an irreplaceable investment in human capital. By late 1943, the Red Army had accumulated a substantial core of veteran tankers who'd survived multiple engagements, many of them owing their lives to the fact that German shells had bounced off their T-34's sloped armor instead of penetrating. These veterans trained newer crews, passing on lessons learned in combat. The organizational experience accumulated by Soviet tank units between 1941 and 1943 became a significant advantage in itself, and much of that experience wouldn't have existed if the T-34's armor hadn't kept crews alive long enough to become experienced. Konstantin Sergeyev received the Order of the Red Star in November 1942 for his contributions to tank production, though the citation didn't specify what those contributions were. He continued working at the Nizhny Tagil factory throughout the war, training welders and refining procedures. After the war, he returned to Leningrad and worked in shipyard construction until his retirement in 1957. He died in 1964, and his obituary in Pravda identified him simply as a veteran worker who contributed to the Great Patriotic War effort. The technical details of his welding procedure were declassified gradually over decades as Soviet industrial secrecy loosened. By the 1970 seconds, Western metallurgists studying Soviet tank design had identified the T-34's welding techniques as a significant but underappreciated innovation. Papers published in materials science journals analyzed the multi-pass procedure and its effectiveness at managing residual stress in acute angle joints. But even these technical analyses rarely mentioned Sergeyev by name. The procedure had become so thoroughly institutionalized that its origins had been essentially forgotten. Modern tank design has moved far beyond the welding techniques of the 1940 seconds. Contemporary main battle tanks, like the Russian T-14 Armata, use modular armor arrays, composite materials, and advanced welding processes that would have seemed like science fiction to Sergeyev. Laser welding, electron beam welding, and friction stir welding have replaced manual arc welding for many critical joints. But the fundamental principle that Sergeyev proved, that properly executed welding procedures can join armor plates at extreme angles without creating weak points, remains embedded in every modern armored vehicle design. The legacy extends beyond tanks into broader industrial applications. The controlled heat input, multi-pass welding techniques that Sergeyev developed for sloped armor are now standard practice for any application where joint integrity under impact loading is critical. Pressure vessels, ship hulls, aerospace structures, even bridge construction. The American Welding Society's specifications for critical weld joints incorporate principles that trace directly back to the work done by welders like Sergeyev who figured out how to manage residual stress and heat-affected zone properties through careful control of the welding process. There's a broader lesson here about innovation under constraint. Sergeyev wasn't trying to revolutionize welding, metallurgy. He was trying to solve a specific problem: how to join armor plates at angles that everyone said were impossible to weld. He succeeded not through theoretical insight, but through practical experience, understanding how steel behaves under heat, how different welding pass sequences affect cooling rates, how to balance thermal mass when joining plates of different thicknesses. This kind of innovation doesn't come from research laboratories or advanced degrees. It comes from craftsmen who understand their materials at an intuitive level, who can feel through their hands whether a joint will hold, and who are willing to try approaches that formal engineering analysis says won't work. Sergeyev's technique violated Soviet welding standards because those standards were written by people who hadn't actually tried to weld sloped armor at production scale. He did it anyway because he knew it would work. The T-34's success in combat vindicated that craftsman's intuition. Between 1941 and 1945, Soviet factories produced approximately 84,000 tons, 3-4 tanks, more than any other tank model by any nation in World War II. Every one of those tanks incorporated welding techniques that Soviet metallurgists had initially declared impossible. Every one benefited from the armor protection that those welding techniques enabled, and thousands of Soviet tankers survived battles they might not have survived in different tanks, because a welder from Leningrad refused to accept that sloped armor couldn't be reliably welded. The Germans learned this lesson the hard way, taking casualties from T-34 seconds throughout 1941 and 1942, while their engineers insisted that Soviet industrial methods couldn't possibly produce reliable sloped armor joints. By the time German designers adopted similar approaches with the Panther, the Red Army had already accumulated 2 years of combat experience operating tanks that their enemies couldn't reliably kill from the front. In post-war interviews, German tank commanders who'd fought on the Eastern Front frequently cited the T-34 as the most difficult opponent they'd faced. Not because it was more heavily armed than German tanks, the Panther and Tiger both mounted superior guns. Not because it was better protected, overall German heavy tanks had thicker armor. But because the combination of sloped armor, adequate armament, good mobility, and sheer numbers made the T-34 a threat that couldn't be safely engaged under most tactical circumstances. Field Marshal Erich von Manstein, commanding German forces on the southern sector of the Eastern Front, wrote in his memoir that the T-34 represented a technological leap we had not anticipated. Its sloped armor made our standard anti-tank weapons ineffective, forcing us to develop entirely new tactical doctrines and weapons systems. This adaptation consumed time and resources we could not afford. What von Manstein didn't know was that the technological leap he described was enabled by a welding technique developed by a single craftsman working in a Soviet tank factory. The sloped armor that German soldiers learned to fear was only possible because Sergeyev had figured out how to weld it reliably at production scale. Without that innovation, the T-34 would have remained a promising design that couldn't be built another paper tank that never influenced the actual course of the war. The mathematics of the T-34's impact on the Eastern Front are staggering. Between June 1941 and May 1945, the Red Army fielded approximately 60,000 tons 34 seconds in combat operations. These tanks participated in virtually every major engagement on the Eastern Front, from the defense of Moscow in 1941 to the final assault on Berlin in 1945. Estimates of German tank and anti-tank gun losses attributable to T-34 seconds vary widely, but even conservative figures suggest that T-34 seconds accounted for at least 30,000 German armoured vehicle kills, roughly equivalent to the entire German production of all tank types during the war. The force multiplication effect of sloped armour is visible in these numbers. A T-34 that survived an engagement because German shells ricocheted remained available for subsequent engagements. German tanks that might have achieved kills if their shells had penetrated instead had to retreat or be destroyed by return fire. The cumulative effect over thousands of engagements and 4 years of war was decisive. Soviet industrial production enabled this effect, but the production wouldn't have mattered if the tanks hadn't been effective in combat. The T-34 was effective specifically because its armor protection allowed it to close with and destroy German tanks that theoretically had superior guns. That armor protection existed because Sergeyev's welding technique made sloped armor practical for mass production. By the end of the war, sloped armor had become standard for virtually all new tank designs worldwide. The American M26 Pershing, the British Centurion, and post-war French and Chinese designs all incorporated sharply sloped frontal armor. The principle was now universally recognized. Angle your armor as steeply as possible to maximize effective thickness and deflection probability. But recognition of the principle didn't automatically solve the manufacturing challenges. Western tank designers in the late 1942 and 1950s had to independently develop welding procedures for sloped armor joints, often rediscovering techniques similar to Sergeyev's through their own trial and error. The Korean War saw early production M46 Patton tanks suffer from weld quality issues, similar to the early Panthers joints that cracked under stress, allowing water infiltration and component damage. American engineers solved these problems through improved welding specifications that incorporated controlled heat input and multi-pass techniques, essentially the same solutions Sergeyev had developed a decade earlier. The technological history here is a reminder that manufacturing know-how is often as important as design innovation. The T-34's designers created an excellent tank on paper, but it took craftsmen like Sergeyev to make that paper design into something that could be built by the thousands, and that would hold together under combat conditions. The welding procedures he developed were every bit as important to the T-34's success as Koshkin's overall design. But while Koshkin is remembered as the T-34's creator, Sergeyev remains virtually unknown even among historians who study Soviet tank development. This pattern of anonymous craftsmanship, enabling famous designs, appears throughout industrial history. The engineers who receive credit for breakthrough products are building on the work of machinists, welders, assemblers, and technicians who solve the practical problems that make manufacturing possible. Sergeyev's story is remarkable, not because it's unusual, but because we happen to know enough details to reconstruct how his individual contribution shaped a historically significant weapon system. Most such contributions remain forever anonymous, visible only in the final product's performance, not in the historical record of who made that performance possible. The thousands of Soviet welders who learned Sergeyev's technique and applied it to tens of thousands of tanks never received individual recognition, but collectively they executed the manufacturing process that gave the Red Army its most important weapon. Every T-34 that rolled off a Soviet production line carried their work into combat. The same pattern holds for the German, American, and British welders, who eventually learned to weld sloped armor on their nation's tanks. Their names don't appear in history books, but their skill made possible the vehicles that did. The Panther, Pershing, and Centurion existed because unnamed craftsmen figured out how to join thick steel plates at acute angles without creating weak points. This is how industrial warfare actually works, not through genius designers alone, but through the collective competence of workers who can execute complex manufacturing processes at scale. Konstantin Sergeyev happened to be the specific individual who solved a critical problem at a critical moment for Soviet tank production. He did it using skills learned from German instructors in the 1920 seconds, applied to a Soviet design challenge in the 1940 seconds, creating a solution that eventually influenced tank design worldwide in the decades after the war. His contribution was simultaneously personal, the specific welding procedure he developed, and impersonal, in that similar solutions would likely have been found eventually by someone else if he hadn't existed. But for the Soviet tankers who fought in T-34 seconds between 1941 and 1945, the timing mattered enormously. They got effective sloped armor protection immediately, not eventually. German shells bounced off their tanks starting in June 1941 because Sergeyev's welding procedures had been incorporated into production starting in late 1940. If that solution had come later, if Soviet factories had spent 1,941 and 1,942 trying to make sloped armor work, thousands of additional Soviet tanks would have been destroyed and thousands of additional tankers killed. The counterfactual is worth considering. What happens to the Eastern Front if the T-34 enters production with vertical armor because nobody solved the sloped armor welding problem? Soviet medium tanks would have been vulnerable to German 50mm guns at all ranges. Soviet tank losses would have been substantially higher throughout 1941 and 1942. The Wehrmacht's panzer forces, already more experienced and better coordinated than Soviet tank units in the early war period, would have achieved even more lopsided kill ratios. Would this have changed the ultimate outcome of the war? Probably not. Soviet industrial capacity and manpower reserves would likely have prevailed eventually, even with less effective tanks. But the cost in lives and time would have been significantly higher. The battles around Moscow in December 1941, where T-34 seconds played a crucial role in stopping the German advance, might have gone differently. The defense of Stalingrad, where Soviet armor helped contain German forces in urban fighting, would have been more difficult with less survivable tanks. These speculations highlight how much can depend on seemingly minor technical decisions. The choice to pursue sloped armor despite welding challenges, and the successful development of procedures to make that choice viable, influenced the course of the largest military conflict in human history. Sergeyev's work didn't determine the war's outcome, but it affected when and how that outcome was achieved, and it influenced how many people survived to see it. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.